Why extraterrestrial life may not seem entirely alien. The zoologist Arik Kirschenbaum argues that because some evolutionary challenges are truly universal, life throughout the cosmos may share certain features. Arik Kirschenbaum, a zoologist and animal communications researcher at the University of Cambridge, thinks that the evolutionary forces that shape life on Earth will produce many similar features in extraterrestrial life. On the website for the Department of Zoology of the University of Cambridge, the page for Arik Kirschenbaum lists his three main areas of research, one of which stands out from the others. Kirschenbaum studies wolves and other canids, dolphins and cetaceans and aliens. Granted, science hasn't yet found any aliens to study, but Kirschenbaum says that there are certain things we can still say about them with reasonable certainty. Topping the list, they evolved. The bottom line: why animals do the things that they do, why they are the things that they are, is because of evolution, said Kirschenbaum, a lecturer and director of studies in the natural sciences at the university's Girton College. He argues that evolution is a universal law of nature, like gravity, and that studies of plants and animals here can therefore tell us something useful about potential inhabitants of worlds far beyond Earth. He finds evidence for this in the process of evolutionary convergence, in which unrelated lineages of organisms evolve similar features as adaptations to similar environmental challenges. It's an argument he presents in detail in his new book, The Zoologist's Guide to the Galaxy: What Animals on Earth Reveal About Aliens and Ourselves, which draws on comparisons of animals' physical adaptations, as well as his own research and that of others into animal communications. Quanta recently spoke with Kirschenbaum at his home in Cambridge via video conference. The interview has been condensed and edited for clarity. You're a zoologist, you study life here on our own planet. What made you want to write a book about alien life? When zoologists study life on Earth, we're studying mechanisms. We're studying how life became the way it is. And because evolution is the explanatory mechanism for life everywhere, then the principles that we uncover on Earth should be applicable in the rest of the universe. Thinking about how life on other planets evolves and behaves is just a natural extension of my work with animals on Earth. If we discovered a lost island on this planet, we'd be examining its animals from the perspective of what we know about the evolution of life in general. You can be sure that if we discovered alien life on another planet, we'd be using the same methods to ask why they look and behave the way they do, and how they evolved. Thinking about how life on other planets evolves and behaves is just a natural extension of my work with animals on Earth, Kirschenbaum said. You argued that natural selection, the key mechanism behind evolution, is inevitable, and that it applies universally. What makes you so confident about that? No planet will have a complex form of life that popped into existence all on its own. Whatever life is like on an alien planet, it must have begun simply. Now, it could be that it remains simple, that's possible. Probable, even, on many planets. But if life is to achieve any kind of complexity, the only way that complexity can accumulate is if favorable changes and innovations are retained and unfavorable ones are lost, and that's precisely evolution by natural selection. One of the key ideas in your book is the notion of convergent evolution. What is that, and why is it important? If you observe two animals with similar features, feathers, for instance, you might presume that they inherited them from a common ancestor, the feathered dinosaur that was the ancestor of all modern birds. That's just regular evolution, where children have similarities because they inherit the characteristics of their parents. But sometimes you see animals with traits that they couldn't possibly have inherited from a common ancestor. For instance, the wings of birds work in pretty much the same way as the wings of bats. But the common ancestor of birds and bats was a small lizard-like creature that lived over 300 million years ago, long before even the dinosaurs. It certainly didn't have wings, and the large majority of its descendants, including elephants and crocodiles, don't have wings, thankfully. So those wings must have evolved separately in different lines of descendants. Sometimes this convergence of traits is for something obviously useful, like wings. But sometimes convergence produces bizarrely similar creatures that share so many characteristics, it can be hard to believe they're not closely related. The recently extinct thylacine, a large predatory marsupial native to Tasmania and mainland Australia, for example, could easily be mistaken for a peculiar breed of dog, but it's much more closely related to a kangaroo. And yet living a life similar to that of modern coyotes or jackals meant that it evolved many similar characteristics convergently. The laws of physics and biomechanics constrain the ways that animals can conceivably evolve mobility on this planet. And so we can expect these constraints to be operating everywhere in the universe, Kirschenbaum said. You're arguing that wherever organisms confront similar environmental challenges, they may come up with similar adaptive solutions. And you expect to see this throughout the universe. Consider flight, since that's the most famous example of convergence. If you live on a planet with an atmosphere, or even with an ocean or some other fluid, if you want to get from one place to another through that fluid, there's only a handful of ways to do it. You can jump. You can float, if you're lighter than the medium that you're in. The only other way is aerodynamically, with a wing, to generate lift. Those are the mechanics of moving through a fluid medium. On Earth, flight evolved 4 different times in 4 different groups, in birds and bats and pterosaurs and insects. The fact that they all use wings isn't because they evolved on Earth, it's because it was advantageous to fly, and wings are just about the only way to fly. And so we can expect these constraints to be operating everywhere in the universe. How far can that insight take us, though? As you said, organisms anywhere that need to fly are likely to evolve wings. But the wings of bumblebees, bluebirds and bats are very different. Yes, bat wings and bee wings are different, but only in detail, not in principle. Both consist of a membrane supported by rigid structures. Both generate lift by creating airflow over that membrane. In fact, the main difference between bee wings and bat wings is not in their structure, it's in the way they use them. The small size of insects means that they cannot simply flap their wings like bats and expect to fly. They need to buzz, generating lift both on the forward stroke of their wings and on the backward stroke, something that neither birds nor bats do. So rather than the diversity of implementations on our planet confounding our comparisons, we can actually be more confident about our predictions, because we can see how tightly constrained these solutions really are. Yes, birds, bats and bees have different wings, but they've all achieved the same end result, an aerodynamic wing, despite the hugely different physical constraints acting on them. Coincidences of evolutionary and even cosmic history will always affect the details of animal shape and appearance. We have 4 limbs only because it was a 4-finned fish that crawled out of the sea almost 400 million years ago. We could easily have had 6 limbs, or even 8, if evolutionary history had played out differently. So there will never really be close similarity between us and our equivalent species on an alien planet. But some things are just so tightly constrained that there aren't really many alternative ways to do things. Stephen Jay Gould, the noted paleontologist and evolutionary theorist, famously wrote about the idea of replaying the tape of life and letting life evolve over again. Gould imagined that the outcomes would be different. We would be unlikely to end up with Homo sapiens, for example. But it sounds like you're arguing that, while any one specific outcome is unlikely, the same kinds of innovations would crop up again and again. That's absolutely right. There's this big argument between Stephen Jay Gould and Simon Conway Morris of Cambridge. Is it going to be different every time you replay the tape? Is it going to be the same every time? But obviously, the correct answer is, it will be different, but many things will be the same. And the things that will be the same are those things that are constrained either by the laws of physics or by the laws of evolution. There are mathematical rules that govern the way evolution works. One of the things I talk about in the book is sociality. Sociality evolves because of the particular characteristics of evolution, not because of physics. Those sorts of things are constraints too. They will continue to be constraints no matter how often you replay the tape of life. What kinds of constraints or pressures drive sociality on Earth, and how might we expect them to apply elsewhere? Cooperation and communication are very widespread on Earth. At first glance, that's perplexing. Why would two organisms cooperate? But you don't have to think about it for very long to realize that they'll cooperate if they both benefit from it, and that rule will apply on any planet. It could be that animals on other planets will cooperate simply for mutualistic reasons, because it benefits them both. But much of the cooperation on Earth, much of the sociality, is driven by relatedness. We cooperate because we're related. We feed our children, we help our parents, we befriend our siblings. All of these things are well founded in evolutionary theory. The way our characteristics, our traits, our behaviors are passed down from generation to generation is through our genes. And if our genes make us tend to cooperate with our siblings, then we'll be more successful, and so will they, and we'll all pass on our related genes. The trouble is, we don't know what aliens have for genes. So this is something we can't say is quite as universal as some of the other constraints of biology on Earth. It may be that the way that alien life forms are related to each other is completely different, and so their sociality may be completely different as well. Much of your personal research has been on animal communication in wolves, dolphins, and other animals. How did your work in that area inform your thinking? Are there universal features of animal communication on Earth that would apply to understanding alien communications, intelligent or otherwise? Sometimes, common features in very different animals just jump up and hit you in the face. They're hiding under the surface, but when you see them, it's just so obvious. I saw this when I started working with wolves, after previously studying dolphin whistles. When you represent those sounds visually, using a mathematical transformation, called a spectrogram, they look almost identical. Apart from the scale, dolphin whistles are much shorter and higher pitched. So I tried slowing down a dolphin whistle, and lo and behold, it sounded rather like a wolf howl. These two sounds are so different, but they have a similar underlying structure. The question is why? Well, the answer isn't hard to find. Both dolphins and wolves use these sounds for long-range communication in an environment where sounds get distorted and absorbed. Using their kind of varying pitch is the effective way to preserve the information in the message under those conditions. Would the same thing happen on an alien planet? I think that's a perfectly reasonable proposal. What about language? Would intelligent aliens need that? Let's say your species is intelligent enough to want to build a spaceship, or a radio telescope, something complicated. You will have to be able to communicate a very large number of ideas to a lot of other individuals working on it with you. And if you're going to have a communication system that's flexible enough to communicate a very large number of concepts, it will probably be infinitely flexible, and therefore it will meet the definition of language. Communication like human language needs to be complex, but not too complex. That balance between complexity and simplicity is found in all human languages, and in a lot of animal communication as well. One of the most promising directions for Scie research is to look for statistical fingerprints of language in a signal, because it seems likely that some constraints like these operate on intelligent communication everywhere. In your book, you write, curiosity will drive philosophy, social interaction will drive art, and complex communication will drive literature. Really, these traits arise almost inevitably from the combination of intelligent skills that we, and presumably other alien species, possess. It's beginning to sound like these hypothetical aliens are almost human. Some planets are just going to have simple life on them. Many, maybe even most. But let's assume that we found a planet with something we would call intelligent life. No one gets intelligence just because it would be a cool thing to have. Their ancestors must have benefited from that intelligence. If they reached the stage where they can build a radio telescope, then they must have been through the stages where it was advantageous to be curious, where it was advantageous to communicate. But it seems less obvious what survival advantage things like philosophy and art and literature give you. The cognitive psychologist and linguist Steven Pinker has famously argued that music developed as a kind of accident, that it doesn't have survival value on its own. Is it possible that we'd find aliens who have the technological stuff, the rockets and the telescopes, but not the philosophy and art and literature? It certainly is possible. But it doesn't seem likely. Because all of these traits that we take for granted, things like curiosity, communication, language, they didn't evolve so that we could build a radio telescope. They evolved to support our sociality. Our ancestors were singing and dancing and telling stories long before they were writing scientific research papers. Those skills didn't evolve for the purpose of leaving planet Earth and finding aliens. They evolved only because they were advantageous to the society. It's tempting to think that an advanced alien civilization may just dispense with or may have never needed things like philosophy and literature. But they evolved from a pre-technological species. And if that pre-technological species went on to develop all the things that we have now, chances are that they were built on building blocks that served that social purpose, things like bonding between group members, transmission of information and useful ideas between group members. A pre-technological alien civilization could be singing and dancing and telling stories just like pre-technological human civilization did, because it serves the same purpose. Some scientists are skeptical of arguments based on evolutionary convergence, especially where attributes like intelligence are concerned. We marvel that humans, dolphins and octopuses evolved some degree of intelligence, for example, but the three animals have a common ancestry that goes back hundreds of millions of years before they split off from one another. How might you respond to that? Let's consider humans and octopuses. Their common ancestor lived around 800 million years ago. It was a little slime ball. And the descendants of all of those little slime balls are just about every single animal on Earth, with the exception of corals and jellyfish and things like that. The common ancestry of humans and octopuses is shared by almost every creature on the planet. Why are only a few of them intelligent, if they all share that common ancestry? The answer is that these things developed independently. Intelligence is not inherited from that common ancestor. Birds and bats share a common ancestor, sure. But not all of the descendants of their common ancestor fly. Hardly any of them do. They didn't have wings. Wings evolved independently. The idea that the traits we have now are dependent on our common ancestors, just because we have a common ancestor, is not correct. As you know, Scie is beginning to be recognized as a mainstream branch of astronomy, and here in our own solar system we're using robotic spacecraft to search for signs of past life on Mars, and we may soon be exploring Enceladus and other moons. What are some of the key takeaways from your research, for those who are actively trying to find life, either simple life or intelligent life beyond Earth? Related. I think that up until now, that effort hasn't been very relevant. All of a sudden, it's become unbelievably relevant. That's because we're now just about approaching the stage where we're going to have to start to think about what the biology and ecology of alien life is like. And the moment we do that, we have to think about their evolutionary trajectories. I'll give you an example. You'll remember the recent fuss about the signal of phosphine on Venus. Let's say it's real, and that it's indicative of life. The next question is, how did that life evolve? Let's assume we have these floating microscopic organisms in the temperate region of the atmosphere. How did they get there? How did they evolve that complexity? We're coming to the point where we have sufficiently sensitive technology to detect life on other planets. But that doesn't tell us how they got there. It doesn't tell us anything about their ecology, how they interact with the other organisms on the planet, with the abiotic environment. But most importantly, it doesn't tell us how they evolved. And that's the question that astrobiologists have to start thinking about.